everyone and welcome back to my channel A in Economist. So in the previous few videos we have been talking about some of the most important covariance stationary processes, right? This is going to be a continuation of our lecture number 5, where in the previous videos we have learned what is a white noise process, and then we have gone into the moving average process. We have covered moving average process of order 1 and moving average process of order q. We have shown different aspects of them and why we call them covariant stationary in the first place. Now it's time for us to cover this remaining part, that is the MA infinity process, and that is what we are going to do in this particular video, right? So let me start with this. What is MA infinity process? A process YT is said to be an MA infinity process if it can be written as follows, right? Let us see how we can write this YT. As of now, I think you have understood how it should look like. It is alpha plus epsilon t plus theta 1 epsilon t minus 1, theta 2 epsilon t minus 2, so on and so forth. It has no ending. It will go up to infinity, right? Hence the order is infinity. Since we consider infinite lag values, and YT can be written as the infinite weighted summation of all these lag values or epsilon t's, hence it is called a moving average process of order infinity. Now again let me write the compact version of it, that is simply j from 0 to, now it will be infinity, theta j epsilon t minus j, right? Now one thing I forgot to mention here is that epsilon t follows white noise 0 sigma square. This is intact, this is not changing. Theta 0 is assumed to be 1, and this epsilon t follows white noise 0 sigma square. And now in the previous video I have told you how to write the lag operator representation of this expression. So let me do that also. J from 0 to infinity, theta j is as it is, and then epsilon t minus j can be written L to the power j, lag operator to the power j into epsilon t, right? Where this L to the power j epsilon t is nothing but epsilon t minus j for all j and integer, right? So this is what we have. So I have given you how to write the MA infinity process. I have given you how to write it in a compact way and also the lag operator representation of it, right? Simply epsilon t minus j will be replaced by L to the power j epsilon t for all j which is integer, right? Okay. Now how to write this? Again, j from 0 to infinity, we have L to the power j epsilon t, right? Sorry, theta j. Firstly you have theta j and then L to the power j into epsilon t. This is what you have. So what you can write, YT alpha plus capital theta L. This is also I have told you in my previous video. If you haven't watched that, I'll give the link in the description. Check that video out and then come back. And this is the compact format where theta L, this is capital theta basically. Capital theta L is summation j from 0 to infinity theta j L to the power j is the characteristic, it's called the characteristic polynomial. It's called the characteristic polynomial of MA infinity process, right? It's called the characteristic polynomial of MA infinity process, and the similar thing we have done for MAQ process also. We have written it in this format where we have told that this theta L is the characteristic polynomial of MAQ, and the similar thing we have done here also. This is the characteristic polynomial of MA infinity process, right? Now the next thing that we will be going into showing that is this process stationary or not, and if it is stationary, what is the required criteria, right? So let us do that. Firstly, find out expectation of yt. Simply it will be alpha plus summation j from 0 to infinity theta j epsilon t minus j. Now if you take expectation, what will happen? So expected value of alpha is simply alpha, right? And then you write j from 0 to infinity. Theta j is a scalar, so expectation will not be on that. Expectation will be on this expression, because we know the distribution of epsilon t's, right? Epsilon t's we know follows IID normal, white noise 0 sigma square. Not normal, we don't know what is the distribution. As I have told you that white noise does not have any distributional assumption. It is independently and identically following white noise process with this properties only, right? And what will this be? This is basically 0 because the expected value is 0, so it is simply alpha, right? This is simply alpha. It is independent of t, and not only that, it is finite. This is finite, and this is very important that when you are considering MA infinity process, you have to ensure not only the expectation variance and autocovariance are independent of t. This is a prerequisite. They have to be independent of t. Not only that, they also have to be finite quantity, and that is the additional restriction that you have for MA infinity. In case of MA1 and MAQ processes, we only checked for if they are independent of t, but now you have to also ensure that they are finite in nature, right? Okay. Now the second is variance of yt. So it is simply variance of alpha plus summation j from 0 to infinity theta j epsilon t minus j. Variance of alpha is 0. This is just a scalar, so variance will be only on this summation j from 0 to infinity theta j epsilon t minus j. Now we know that this scalar quantities will be squared, right? So j from 0 to infinity theta j squared, and then variance of epsilon t minus j, right? What you have, variance of this is simply sigma square. So that sigma square will come out, and then you will be left with j from 0 to infinity theta j squared, right? This is the expression for variance of yt. Now you can see that this is independent of t. This is fine, but we don't know right now that it is finite or not. Sigma square is always finite. There is no problem in this, but we don't know if this quantity is finite or not. So we'll figure that out in a while. But before that, let us go into the autocovariance, right? Autocovariance of yt minus h. That is basically covariance of alpha plus summation j from 0 to infinity. The process is the same. I am using the same process for all these things. This is epsilon t minus j, and then alpha plus summation j from 0 to infinity theta j alpha t minus h minus j, right? This is what you have. Okay. Now simply h equals to 0 will give you the variance. I am not repeating the reason. You must know this by this time. If you are following my lectures on time series, you must know. And then covariance. Covariance of this when h equals to 1. What you can see here is that alpha and alpha will not contribute in calculating the covariance, so I am writing only these expressions. j from 0 to infinity, theta j epsilon t minus j, and then j from 0 to infinity, you have theta j epsilon t minus h minus j. Right? This is what you have. Now I am giving you a small homework at this point. A small homework where you have to calculate h equals to 2, h equals to 3, and some of the successive terms as much as you like, and then you have to match this expression. Gamma h will be in the form j from 0 to infinity theta j plus h into theta j into sigma square for all h greater than 0. So you don't need to show many terms. Calculate h equals to 1, calculate h equals to 2. Only these two expressions will be enough. So simply just expand this and see the common terms as we have done. I have made a mistake. This is 1, right? T minus 1 minus j, right? Instead of h, you are writing 1 here. So T minus 1 minus j. So simply you need to expand this. If you have seen my previous videos, you will know how to do this. Check for the common terms and calculate these covariance. So do this for h equals to 1 and h equals to 2. You will see a pattern. What will be the pattern? This is the pattern that you will get. I am not deriving this because I know you can do this. So gamma h is simply this expression. This will, come directly from the solution that you will find out. Gamma h is summation j from 0 to infinity theta j plus h theta j into sigma square for all h greater than 0. If you find any difficulty in finding this, you can, let me know in the comment section. I'll derive it in some other video, right? Okay. Now what you can see here is that this expression is also independent of t. So independence from t is not an issue. Here we have seen that expectation is also independent of t and it is finite. Variance, we have seen that this is independent of t, but we don't know is it finite or not. And the same goes for this. This is independent of t, but we don't know is it finite or not. Now how to check for that? This is very important to understand. For finite, what do we mean by finite? This has to be less than infinity. Finite means that the expression variance of yt has to also be less than infinity. And this, right, autocorrelation function gamma h, the absolute value of that has to be less than infinity, and also for the variance it has to be less than infinity, right? This is what we have. Now we will show that from this only you can directly say that variance is also less than infinity. So let me show you how to do this. Now what does gamma h mean? As I have told you, gamma h is this expression. What will be the absolute value? You know that this is finite, right? Sigma square is finite, so this expression you have to check, is it finite or not. So simply do this, 0 to infinity, write j plus h into theta j, and you need to show that this is less than infinity, right? This has to be finite for this to be finite. Now how will you show this? For that we will use something called the Cauchy-Schwarz inequality. Cauchy-Schwarz, Schwarz. Many of you must know what is this Cauchy-Schwarz. You must have learned it in your statistics course. We use something called the Cauchy-Schwarz inequality. What does this inequality say? This inequality simply says that summation I from 1 to n ai square summation I from 1 to n bi square is always greater than equals to summation I from 1 to n ai bi whole square. Right? This is what is known as the Cauchy-Schwarz inequality. It says if ai and bi are scalar terms, so ai is in this form a11, a12, A1n, and bi is in this form bi is in this form b11, b12, and b1n, right? So in this format, so it is a vector, basically a vector. So ai and bi are two vectors, then you can write in this way: I from 1 to n, ai square into bi square. So this product will always be greater than equals to summation ai bi whole square for all I. And this, I hope you know, this is known as the Cauchy-Schwarz inequality, and now we will apply this Cauchy-Schwarz inequality here to show that this is less than infinity. So for that, simply take this to be ai as of now for our purposes, and take not the summation, this expression, take this to be bi, right? Take this to be ai and then take this to be bi, and then simply apply this. Let me do that. So you will get summation j from 0 to infinity theta j square. So ai square basically, right? ai is theta j and bi is theta j plus h. Okay, let me, this is theta j and bi is basically theta j plus h, right? And then you apply the Cauchy-Schwarz. So this is the first term into summation j from 0 to infinity theta j plus h square. This should be strictly greater than summation j from 0 to infinity. Then you have theta j plus h whole square. Okay, now if you see, this is the ACF square basically. This is mod value, this is mod value, and if you take the square root now on both sides, what you will get? Square root, this will give you mod of this, right? Square root, right? You are taking the square root on both sides, so this will be mod of this. This is strictly less than equals to root over of, let me remove this. This is j from 0 to infinity theta j square into summation j from 0 to infinity theta j plus h whole square, right? Okay, now what will be the criteria? So you see, we have got the expression for gamma h here, right? Left hand side is the expression for this gamma h or mod of gamma h, whatever you want to call it, is less than equals to this expression. Now for this expression has to be less than infinity, right? In order to be to have ACF to be a finite quantity, this strictly has to be less than infinity. And when this quantity will be less than infinity, if individually this and this will be less than infinity, right? So this quantity also has to be finite, that is less than infinity, and this quantity also has to be finite or less than infinity, right? I hope this is absolutely clear. It's very simple that for the product to be finite, individual quantities has to be finite. If any of them is, you know, infinity, then the product will also be infinite. So the simple logic here is that individually both these terms has to be finite. This is finite, this is finite. So combining, what you can see is that MA infinity process is stationary if and only if this thing holds. Summation j from 0 to infinity theta j square, this expression is less than infinity. This is what I am seeing. This is less than infinity, and if you change the suffix, it doesn't matter. If theta j square is less than infinity, it means that theta j plus h is also less than infinity, right? So this is the criteria. This is the criteria that we are interested in. This is the criteria which is known as the squared summability. Squared summability. This criteria is known as the squared summability criteria of, you know, checking stationarity for MA infinity process. One thing you must know is that for MA1 process and for MAQ process, there is no such, you know, criteria, because they are always, for any parameter value, they are stationary. Why they are stationary? Because we have shown that the mean, the variance, and the autocovariance are always independent of t, and that is enough for them to conclude that they are stationary. We are not checking finiteness there. Why we are not checking? Because the order or the degree that we are considering is itself finite. MA1, 1 is a finite quantity. For MAQ, Q is a finite quantity. In the definition, I have mentioned that. So since the order is itself finite, the mean variance and the autocovariance are bound to be finite, right? Because they are only the characteristics of the process that we are defining. If the process itself is finite, the properties also have to be finite, right? But in case of MA infinity process, when we are changing the degree to infinity, we don't know that the properties, what will be the properties of this distribution or this process. So in that case, we need to individually check for the properties and see if they are finite or not. For the mean, it is only alpha, so it is definitely finite. For the variance, yes. Now, important thing is that for the variance, if you see this expression, this is finite, I have told you, sigma square. And this we have by the property of square summability now. This is, let me write it SS. For the square summability, this is the thing we have shown that this thing has to be less than infinity, right? This is what we have shown. This thing has to be less than infinity. So the variance is also finite, right? Since this is less than infinity, this is a finite, so the product is also finite. So this term variance is not only independent of t, it is also finite. And similarly for autocovariance, we have shown that the finiteness holds only if this criteria holds, right? This property is known as the square summability. So for MA infinite process, if the square summability holds, we will say the process is finite. The process is stationary, right? I hope this is absolutely clear. Well, one thing to note here is that although we have shown that square summability is very important to show that process is stationary, although square summability of theta j is good enough to ensure that this process is stationary, but it is not the only criteria, right? It is not the only criteria. Let me write it. It is not the only criteria. Square summability is good enough to ensure that the process is stationary, but it is not the only criteria. We can also put a much stronger condition on theta j's, which is known as absolute summability. Absolute summability will be required when we will go into some other aspects of time series. We will be covering that in this playlist also in some other video. But as of now, you must know that square summability is not the only thing that ensures a process is stationary. We can also put a much stronger condition on theta j's, which is absolute summability, which looks like this. I have already written that for you, that summation j from 0 to infinity mod of theta j is less than infinity. This holds. We call the absolute summability criteria holds. Absolute, why absolute? Because we are taking the absolute values of theta j's and then taking the sum, and then we are checking if this is less than infinity or not. Here what we were doing, we were firstly taking the square of theta j's and then taking the sum, and then checking that if that is less than infinite or not. So this is the difference between absolute summability and square summability. And what is the relationship? Relationship is as follows. This is the absolute summability and this is the square summability. What we can say here is that this is a much stronger condition. This is a much stronger condition than this one. This is weak or weaker condition. This is the absolute summability and this is the square summability. For your convenience, I have written it in this way. So what we can say, absolute summability implies square summability. So the process which satisfies absolute summability will also satisfy square summability, but the converse is not. And you can see this from the definition itself, from the expression itself, that why is it so. If you are, suppose theta j's are very, large quantities, and then you are taking the absolute value. So if some theta j's are negative, you are making them positive firstly, and then taking the square. And if that square is less than infinity, then definitely the square of this and then taking the sum will also be less than infinity. You can take some, quantities for yourself and check that if this holds, this will also hold, but converse is not true. The reverse is not true. Square summability does not imply absolute summability. You can take some numerical values for yourself and check Like this is a stronger condition than this. So in, if you draw the Venn diagram, it will look like this. So this will be the absolute summability, mod of theta z. And here the entire thing will be the weak condition, 0 to infinity theta z square. Right? This is a more strong condition and this is a weaker condition. So the processes which are absolute summable are also square summable, but the processes which are square summable are not always absolute summable, and that is what we are trying to see here. And if you have any doubts, let me know and I'll give you the explanation in more detail. For your convenience, I have given you much more explanation than this. Why this is the case? What is absolute summability? You can take a screenshot of this page and you can read it in your free time. I have given you the definition and also the reasoning that absolute summability is a strong condition because it imposes certain constraints on the growth rate of the coefficients, ensuring that the cumulative effect of the past shock diminishes sufficiently fast. If this condition holds, the process is guaranteed to be weakly stationary, also invertible. Invertibility, I haven't gone into invertibility yet. I will be covering this also in a separate video, so I'm not explaining it here. But as of now, you must remember that absolute summability ensures invertibility also, which is not the case in case of the square summability. Square summability, again, you can take a screenshot. You can pause the video and take a screenshot that it is a weaker condition because it only requires the coefficients decay fast enough for the square of the sums to converge, and it is enough to ensure the variance is or remains finite that I have shown you, but it does not guarantee invertibility or stationarity. So invertibility, specifically this criteria is not satisfied in square summability. That we will cover when we will go into invertibility. And here you have a summary why absolute summability is stronger, because it satisfies both these properties perfectly. For MA infinity process to be invertible, coefficients need to decay quickly enough, which absolute summability guarantees. Square summability alone is insufficient for invertibility. And stationarity, it says absolute summability is associated with weak stationarity, whereas square summability does not provide this guarantee. Right? So in summary, we can say absolute summability ensures both stationarity and invertibility, which is more stronger conditions or properties compared to those ensured by square summability. And this is the thing that I am talking about. And with this, I have covered everything that you need to know about moving average process. I have in detail covered what is MA1 process, MAQ process, and MA infinite process. If you have any doubts from anywhere in these lectures, you can let me know in the comment section. I hope you find this video helpful, and if you want me to keep making these videos, then you can give me a like and thumbs up, and you can drop a comment in my comment section, and it gives me immense motivation to continue making videos like this. And if you like this video, give me thumbs up and do subscribe to this channel, AN Economist. Subscription is absolutely free of cost to you, but it gives me reason to go on, right? So thank you for your time, and in the next video I'll be going into the autoregressive process, and similarly we will see what is autoregressive process of order 1, order P, and so on and so forth, and we will go covering in details of that. So thank you for your time and stay tuned for the next video.